Greetings, Amherst High School Honors Chemistry students. Welcome to Remote Learning 101, COVID-19. Here we go. So I pulled out the worksheet packet for solutions, and we'll get started with it. Let's go to work. So what are mixtures? Physical combinations of pure substances. We know that substances are elements or compounds. This is from our previous unit. We know that mixtures can be physically separated because they're physically combined, and we know that the ratio is not fixed, it's variable. A heterogeneous mixture has a distribution of components that is not consistent, it's not even. Whereas a homogeneous mixture has a distribution that's consistent throughout the sample. That doesn't mean it's 50-50, doesn't have to be equal, it's just consistent, it's even. Down here, this is less important kind of stuff, but we'll cover it now. If you take, for example, mud and put it into water, you have what's called a suspension. If you come back an hour later, the mud will have settled out and went to the bottom. If I take a small amount of milk and put it into some water, I have what's called a colloid. It's cloudy. It doesn't settle out. It's consistent throughout, though. So that's just a couple drops of water, a couple drops of milk in some water. It's suspension, settles out, big particles. Colloids, the particles are about the same size as water molecules. They're not going to settle out. If I take some water and dissolve some salt or some sugar into it, those particles, they're spread out and you can't even see them anymore, so they're really small. Suspensions are cloudy while the particles are suspended. Colloids stay cloudy the whole time. Solutions are clear. That doesn't mean colorless, but it means transparent. If I took some copper 2 chloride and dissolved it into water, it's a pretty spectacular blue, but I can see through it and it's not cloudy. It's clear, but not colorless. Suspensions will settle. Colloids don't settle. Solutions don't settle. I can filter mud out of water. I can't filter the milk out of this beaker full of slightly milky water. If I ran it through filter paper, it looks identical as when I started. I can't filter salt out of salt water. The Tyndall Effect. That's the scattering of light. Here's a laser pointer, right? So there's a little laser. If I take my colloid and shine through, you see the line? That's the Tyndall Effect. If I try that with salt water, no line, no Tyndall. So what is the Tyndall Effect? It's when the particles are big enough to scatter the light. So if I could see the beam, there's a good example. That's why there's a fog machine at rock concerts. It's a whole lot more effective for the lighting. Makes it look great. So, Tyndall Effect, well, while the particles are suspended for a suspension, yeah, they're going to scatter light, but after they settle out, no, they won't. Colloids don't settle, so they scatter light the whole time. Solutions, particles aren't big enough to scatter light. Homogeneous, heterogeneous, suspensions will settle out, that's heterogeneous. Colloids and solutions do not settle out, they are homogeneous. A solution is made up of the solute, what gets dissolved, and the solvent, the part that does the dissolving. So the solution is the combination of both of those. The important thing here is that water is not a solution. Water is, generally speaking, the solvent. Let's talk briefly about different ways to measure concentration. So if we talk about the solution being the solute plus the solvent, for example, if I took 15 grams of salt, NaCl, sodium chloride, solid, mixed it with 100 grams of water, it's not 15% by mass salt. The solution weighs 115 grams. So if I do that math, it's 15 grams of salt over 115 grams of solution times 100. It's roughly 13.0% NaCl by mass. And back to our unit on dimensional analysis, we could say it's 13 unit of mass per 100 of solution. It's 87 waters per 100 of solution, and 13 to 87 part to part. So this was part to whole, other part to whole, and part to other part. I should probably switch the prime. That's fine, but once again, water is a part, not the whole. We've done this kind of stuff. Percent is not the only way to express concentration, but it's one that we'll use a lot. Concentration can be expressed many different ways. Here's percent by mass. We talked about that. But if it's a really low percent, well, 0.00001% is probably not the easiest way to talk about it. Maybe it's parts per million is a better way to talk about it. I mean, percent is really, how many would it be per 100? Parts per million is, how many is it per million? If it's lower than that, you could do parts per billion or parts per trillion. For really low dilute solutions, you can use other measures, which are very similar to normalizing to 100, but you normalize to a million, normalize to a billion, normalize to a trillion. The two important ones here, though, molarity and molality, are ones we'll talk about in much greater detail. All right, so that's video number 1. I'm going to put together a video for several of the expressions momentarily, so stay tuned.